So for the quiz, if you got it, if you're ready, go ahead and turn it in before you go. Otherwise, you can turn it in on Canvas until the end of the night. This time, usually they're going to be due at 11:15, but I'll take this one until the end of the night if you need it. There'll probably only be one more this semester anyway. But just a quick warning, kind of where we are. We're getting really close to the end of the semester, so because of that, I've been pretty liberal with the extensions this semester. I can't really do anything about the final though. So as we get closer, I'm happy to give you a little leeway on things if you need it for certain reasons, but I think it's December 9th is our final. I can't remember the exact date. It's in the syllabus, but I have no control, no flexibility on that. So if that's going to be a concern for you at that time, please let me know as soon as possible. But as we get closer, we're kind of running out of wiggle room. Also, we have the next midterm the final test of the class is a week from today. And that'll cover basically all of chapter 4 and the first 2 sections of chapter 5, which we'll probably finish, if not Wednesday, then certainly sometime Friday. I'm going to change this map. So we have one more test. This will be a week from today. So we got a test on the 22nd. That'll be the last one until the final. I'll post some review materials after class sometime today. From 4 to 5.2, or all of chapter 4, and then 5.1, 5.2. Is about, we're in the middle of 5.1 right now. I think that's all I'm going to tell you. Give me a heads up on your way out, and if I forget, but I definitely want to get those back to you. And if I didn't already say, I'm going to post some more. All right, so let's get after it. Just a little refresher on where we were on Friday. Basically, we're trying to find an area under this blue shaded area. We did it with 4 rectangles. We got a really high with 8 rectangles, and we got a little closer. But we can do better. So here's what I would like to do now. We did 4 rectangles. We did 8. Can I generalize this for any number of rectangles that I want? So instead of saying 8 rectangles, I'm saying n rectangles. So let's think about that. So I'm going to draw just a bunch of really small rectangles in here. And thinking about the way that we've been calculating the areas. So what is let's say I have, if I have n rectangles. How wide is each one of these rectangles going to be? How'd you get 1 over n? Oh, let's just stick with this case, this exact case. Right. So, and kind of backwards here, but yeah, 1 minus 0 is 1. So the entire interval is 1 unit long. So if I divide it up, the n equal this. Each one of those things is going to be 1 n wide. So basically what I'm trying to do, I'm trying to find an area by just adding up a bunch of the areas of a bunch of smaller rectangles, right? So we know that the base width for all those rectangles is going to be the same. It's going to be 1 over n. Are the heights going to be the same for all of these? No. But what is, so let's talk about the very first one. What would x sub 1, x sub 2, x sub 3? If I'm looking at right endpoints again, I guess I did not make that clear, but that's what we did last time. I want right endpoints. What would that first endpoint be of that very first rectangle? What's that? Yeah, but so I have a good idea how we're working up to that. I know how I'm going to get my y values, but first I got to figure out how I'm going to find these x values. So what I'm asking here is this. What is this x value right here? 1 over n. And just to make sure we can see this, what's this next one going to be? 2 over n, 3 over n, and so on all the way, right? So I'm going to have n of these rectangles. They're all going to be 1 over n. And I don't know how tall they're going to be yet, but that's the last one we have to work up to. So do 1 over n, 2 over n, 3 over n. I'm going to generalize this all to x sub I equals I over n. So the way I'm going to get any x value is just take whatever little subinterval I care about and divide that by n, right? Are we okay with me generalizing like that? Okay, and I is going to count from 1 all the way up to n. All right, from there, that's how I get the x values. How am I going to get the heights? Right, so then from here I'll have this, f of x sub I is equal to I over n squared. Are we happy with that? Sebastian? Yeah, so I mean that has everything to do with the fact that, so everything I'm doing right now has to do with this exact situation, right? Let me generalize right now. This specific triangle, this function over that. So I have delta x equals 1 over n, and basically the base height is going to be 1 over n, and my height, the base length is 1 over n, and the height is always going to be I over n squared, right? We okay so far? So basically my area, I'm going to write it like this. The area is going to be, have we seen this symbol before? I don't know if I've used it with you, but sigma, yeah, the Greek letter. Yep, capital sigma, which basically just means I'm going to add up all the stuff that comes to the right here. So keep in mind that area, the way this whole scheme is just about adding up a bunch of smaller rectangular areas. So really what I'm doing is this, I'm taking a bunch of base times height products and adding them all together. The base we said was 1 over n. And the height we said was I over n all squared. So we did not do this with 4 rectangles and 8 rectangles, but if we use this summation notation now, we would get the same numbers. So we got an estimate with 4 rectangles. We got a slightly better one with 8 rectangles. What's kind of the end all be all for this? What is the best estimate I'm ever going to get here? I want to try. I mean, I can't really get to infinity, but I can hopefully understand what this is going to look like as n approaches infinity. So I would really like to write this as limit. This area is equal to this limit. The limit as n goes to infinity of this summation. So hopefully you can see that, the more rectangles I make here, the better my estimates are going to get to what the actual truth is, and they're going to get smaller and smaller, right? So I think, did we agree last time that these are always going to be an overestimate the way that I'm doing this? Yeah. So my estimates are going to get smaller and smaller and smaller until they hopefully get to what that true estimate really, or that true area really is. So any questions on how I built up to this before we actually go trying to evaluate that? Go ahead.
Two things.
Yeah.
I is, you said any number?
I is what's called the index of its summation. So basically the way this notation works is, so on the bottom this is I equals 1. Yeah. That's the beginning value. So I have 1, 2, 3, 4, 5, all the way up to whatever it is. We did this last week. In one case, we had this 4. And then at the top of the signal just tells you what the last I want that to be so anything else like set notation? That's essentially that's the base length, because all of these rectangles are going to have equal width. Answer this: how basically how long is each one of those rectangles going to be? Because so basically, the I over n squared, that is that's going to change from rectangle. So yeah, the width is 1 over n. And that won't vary, so it doesn't have that I in it. The height is going to vary, which is why it has the variable I. Oh, yep. Yep. All right. Any more questions about this thing before we go ahead?
You explain summation notation?
Yeah, so the way this thing works is, and let me give a kind of a specific one up here. I'll just do a real basic one. I'll say I equals 1. I'm going to count up to 5. And what I'm going to be adding together is just I. So when I equals 1, actually, maybe I should do I squared so make it look a little different. When I equals 1, what's going to come out? Like what's going to be, sorry, when I equals 1, what's I squared? 1. When I equals 2, so basically, I'm going to get these 5 numbers: 3 squared, 4 squared, 5 squared. Once I have those 5 numbers for the 5 values of I that I actually care about, then I'm going to add them.
Okay. And so it's, you add the result of the function for each I value.
Right. So in this case, I mean, this I squared thing is just, this is just an example. What I'm really interested in is trying to find an area. Model it as a rectangle. Find the area of those little rectangles. And then add all the little areas. Okay. So that's why I'm not taking the area of one thing, I'm taking the area of how many things? N things. And then once I take all those areas, I'm going to add them all together. Yeah, this thing, just for completionist sake, I think that's 55. More questions about all right. So now that we have this thing, let's find the area. So I know the area is this. The limit as n goes to infinity of this sum from I equals 1 to n of I over n squared times 1 over n. So now we can start simplifying. What's the variable of that summation notation? It's actually not n, it's I. But what's the variable as far as the limit operator is concerned? That's n. So here's what I can do. Because n is a constant as far as that summation is concerned, I'm going to take advantage of that fact. So let's do a simplification here. Multiply a bunch of stuff out. From I equals 1 to n of I squared over n cubed, right? But I can do this. I can pull that 1 over n cubed out of the summation. Because as far as the summation is concerned, that's a constant. We okay so far. So go ahead. Just simplify it. So this will be and then you the base width of the rectangles is not very. So if you wrote I over n for any of the base widths, it should be a constant 1 over n. All right, so I'm going to do a little hand waving here and ask you to take this on faith. But I know that if I were to add up the first n square numbers like that, it's going to come out to this. So I got my 1 over n cubed, but this is going to come out to n times n plus 1 times 2n plus 1 all over 6. Which is something I could prove, but I don't think it's worth our time to go through that. It's pretty long. Any questions so far about where we are? Yeah, I'm making sure I got that formula right. Yeah, okay. Oh yeah, I'm not going anywhere. So this is now a limit I think we can deal with. One quick thing I can do is this. So the limit as n goes to infinity of 1 over n squared times n plus 1 times 2n plus 1 over 6. Can I evaluate that limit now, Jordan? Oh, now put the thing there. And then we'll just do it's not hard to do, but it's a long way to go. Anything else?
We have to know how to do that.
No, no. All right, so can we evaluate this limit? So I'm going to do this. I'm going to multiply top and bottom, by numerator and denominator, both by 1 over n squared. And that allows me to rewrite like this. Limit as n approaches infinity of 1 over 1 times 1 plus 1 over n times 2 plus 1 over n all over 6. That's all kind of so the area underneath that unit long interval underneath the parabola comes out to be 1/3. So we could have done 16 rectangles and 32 and just kept getting closer and closer. But being able to take that limit as n goes to infinity, we get the area exactly. Meter, something like that. So I mean, we weren't very close, but for me, even just did as few as 8 rectangles. So as n goes to the numerator up there, you're gonna get 1 times 2.
Oh, 1 times 2.
Yeah. So yeah, the 1 over n's, those are gonna both go to 0. You get 1. Yep. Go ahead.
Your second function, limit is n function p 1 over n squared times that numerator is whatever the n. That's no, the previous one.
Oh,
Okay.
question. This one here. Taking the limit, right? Yeah. So the only way we're in. Keep them coming. What else? Jordan. Sure. So basically what I did was this. If I can zoom into this thing here. Just the numerator. N plus 1 times 2n plus 1 times 1 over n squared. Basically what I did was this. I called this n plus 1 over n times 2n plus 1 over n. So I don't have to, so I mean, I can kind of divide up that 1 over n squared any way I want. So so basically what I did was I thought about it in terms of this 1 over n times 1 over n. Because that's what 1 over n squared really is. But yeah, I admit I did that a little quickly. And then it's just a matter of dividing. 1 plus 1 over n, and then 2 plus 1 over n. The area ended up being 1/3. Kind of a long way to get there, but we can find it exactly, even though we don't have any idea what a good name for that geometric shape is or how to find those areas. So how do we find area in general? We did a very, very specific case. Let's kind of zoom out and do something more general. So the area A of that region S, so we had that blue shaded region under a graph of some continuous function f, and this is a really important part here. The function must be continuous for us to find that area. Otherwise, a lot of the things we just did would have gotten violated. Is the limit of the sum of the areas of the approximating rectangles, and that's kind of what we did, right? We just took, rather than looking at it in terms of 4 rectangles or 8 or 30, whatever, we're trying to see what happens as that limit, or as the number of rectangles runs to infinity. Basically, here's a mathematical representation of what we just looked at. So the area is equal to that limiting sum. As I start adding infinitely many rectangles together, sorry. And I'll go ahead and translate down here for the in terms of summation notation. One thing I will point out while you're writing this down is notice that I have like on all the x values. So we took the right endpoint. There's nothing saying that we have to take the right end or the left end, or even that you have to take the same points on every rectangle. But you have to choose something. So those asterisks represent that you're sampling a height from that rectangle, like from that function somewhere. It could be the left, it could be the right, it could be the middle, it could be the highest or lowest. I mean, you have a lot of choice there. But then those choices start to go away as you make those intervals narrower and narrower. No, R is a single. And basically this process is what's called a Riemann sum. So the German mathematician who first formalized it. So because of that, his just like the number E, the guy who discovered it, his last name starts with E, so that's why it's called that. Anything else about this definition?
That's all the definition of a Riemann sum?
Specifically define an area. Riemann sum's a little more general, which we'll get into, but yeah. The biggest difference is that a Riemann sum can have negative values in it, which to talk about a negative area is kind of meaningless. Anything else? All right. So let's apply this to a different function, different interval. I want A to be the area of a region that lies under that graph between the closed interval 0, 2. So first thing I want to do is to find this. Let's set up that area sum. Just in general, we're not going to be able to evaluate this one because we don't have that many avenues for evaluating summation notation to infinity, but we can at least set that up. So I want to find the area. I'll remind you of this general form again. I want to sum up n rectangles, and actually I forgot something really important, the limit as n goes to infinity of this sum of n rectangles. So we should think about how to fill in these pieces here. One thing I don't know if I've said in the previous title, break this up into, your goal is to talk about infinitely many rectangles. Doesn't really make sense to talk about those intervals. So we can think of delta x as a constant. How wide is a single rectangle going to be in this case? Heard something, but I couldn't tell what it was. Why would it be 2 over n? Right. So it's all a matter of, how big is the interval? In this case, and by the way, I'm saying 2 minus 0 because I won't always give you intervals that have 0 as one of the ends. But basically, you're taking a total length of 2 and dividing it up into n equal shares. So our delta x is 2 over n. Now I want to find right endpoints. Which is kind of what we've been doing the whole time. So what should if I want to sample always at the right end of one of these little subintervals, what should I replace f of xi star with? Let me say it this way. What if I was just doing one rectangle? Then what value of x would I be looking at? 2, right? Just the far right end of the interval. if I was doing 2 rectangles, what would the first value of x be? 1. So I'm just looking at basically the right end of the first interval and kind of generalizing from there. So maybe the first thing we should do, or the next thing we should do, is this. Let's generalize this. I know that x of 1 is going to be equal to, or maybe I shouldn't assume that we know that. When we have n rectangles, some general n, where's the first value of x going to be? No, that's the left end.
Oh, in this case, it'd be
Not if I have n rectangles. Like 2 is the very far right end, right? It'd be 2 over n, basically. And that's another good thing to think about, this delta x. Basically, that's how far to the right you're going every time, right? 2 over n. What's the second interval going to be, or the second x value to sample at? 4 over n, then 6 over n. Can we use that to generalize for any x, or any I mean? 2i over n. I'll go ahead and pause there because that might be mysterious. Are we okay with, go ahead.
We also generalize.
Delta x I over n. Let's take a look at it. X, so Ben is asking if we can say this. Can we say that x sub I is equal to delta xi over n? Is that always going to be true? I see a head shake. Why would that not be true? No, I think that's true for any number of rectangles. I think that would work. That's going to work in this situation. Yeah. So we're going, that's, and hopefully you see that pattern: 2 over n, 4 over n, 6 over n. Oh yeah. Okay. So now I think we've repaired it, right? Is this going to be true all the time? Not just for this example, but all the time? What if the interval was like from -2 to 2? It's still a change of x, but does it start at 0? Not if my interval is from like -2 to 2. So I'm glad this came up, because here's another way we can generalize this. And maybe I'll build up to it. Our first interval is always going to be this: a plus delta xi. So far I'm kind of using this into this. So every interval we look at some point that started at this. So because of that, you have to say on our first right endpoint is 1 delta xi. Or I mean, you're not universally going to have that. You're going to sometimes have to think about what your interval is. In this case, I have a equals 0, b equals 2. Jordan?
So, oh yeah, so it's the minus 0.
No, so let me give you an example here. What if I had the interval from -4 to 6? In that case, and I had n rectangles, what would the delta x be? It'd be 10 over n. Because so this right here is the most general case. And maybe I wasn't clear enough about that. In this case, xi is always equal to delta xi. I can always find the ith value of x by doing that. Because in this case, my interval, the full interval begins at 0. But I will eventually give you intervals that don't begin at 0. So in that, what's that? Right.
So,
So this case, let's follow that to its conclusion. In this case, delta x would be 10 over n, right? What would x sub 1 be? It would not just be 10 over n because that's way far to the right of where I want to start. It'd be negative 4 plus 10 over n. Because think of it this way. So in this new situation that we came up with, the very left end of my interval is negative 4. But I'm sure that somebody else needs this. So if I start at negative 4, that's my very left end of my interval, and all my rectangles are 10 over n wide. I need to move 10 over n. That'll be my first rectangle. The second one will be, so my second sampling point will be negative 4. Then plus 30 over n. All the way to the right. Okay. Can we come back to e to the negative x now? So I think we're good with delta x being 2 over n for this example. What should I do to replace f of x sub I star? Did we already say, oh, so we said, oh yeah, we said x sub 1 equals 2 over n, or 2 over n. So f of x sub 1 would be f of 2 over n. What is f of 2 over n? E to the negative 2 over n. So let's just try to jump into generalizing that. What is f of x sub I star? So remember, we said this was 2i over n, right? But for any value of I, the x value we care about is 2i over n. Well, okay, so I'll put this in here. A plus, I mean, yeah, it is f of a plus, but in this case, our a is 0. So I'll do this. E to the 0. I don't know why I said negative 2 over n. Oh, yeah, I did. A to the negative 0 plus 2i over n, which just comes out to be e to the negative 2i over n. In this case, a is 0 because that's the far left end of our interval. Yeah. Then you'd have to offset it to the left. Yeah, you'd have a different change in x. Yeah. So I mean, all these things are totally situational. We're getting there. So, that's what we want to replace with f of xi star. So it'll be e to the negative 2i over n times our delta x, which was 2 over n. Just to kind of give you a little hope, I know all of this seems mysterious right now, but I'll promise you this. If I were to ask you to find this area at the end of the week, I'm in it. So right now, let's just it's terrible. That was the general case. Any questions about how we got there? All right. So kind of a separate issue. I want to estimate this area taking midpoints with 4 intervals. So in this case, I'm going to do a summation notation, but I don't care about the limit, I'm just going to go from 1 to 4. But I can use a lot of these same ideas here. I'm still going to sample at the function at some places. And I'm going to multiply that height, that f of xi star, times my new delta x. What's my delta x going to be this time? So what's n this time? Remember, the n is the number of rectangles I want to use. And in this case, I'm not trying to limit n. I'm just saying that n is equal to 4. So how long is my full interval? Still, yeah, it's two units long, right? And I want to divide that into 4 equal pieces. So in this case, I'm going to say my change in x is just going to be 1/2, half a unit. All right, but I want midpoints. So what's my first value of x going to be? If I want the midpoint of the first subinterval, 1/4. So x1 is going to be 0.25. What's x sub 2 going to be? So keep in mind, we can use this thing here. So we can say x sub I is equal to a, which is 0. What's my delta x? 1/2 times I. Here's the only difference. We wrote that thing for midpoints, right? Or we wrote that one for right endpoints. This time we're going midpoints. So we have to be a little more careful, but the key idea is this: how far apart are each of my sampling points? They're half apart, right? Yep. So this first one's going to be, e to the negative 0.25 times 1/2 plus e to the negative 0.75 times 1/2 plus e to the negative 1.25 times 1/2 plus e to the negative 1.75 times 1/2. So each one of these things represents a small rectangle. If you find those 4 areas and add them all up, that's going to give us a pretty bad estimate, but still, we can eventually generalize that to get to something exact. On the far left? Yeah, how do we get that 1/2? Someone remind us. Delta, yeah, so that's delta x over n. Right. So remember, in our case, our interval is 2 units long. So in general, the way that we divide the full width of the interval by n. In this case, we have almost so dividing 2 units of length by 4 to get 1/2. Each subinterval is 1/2 unit long. Go ahead. Yeah, but where? Yeah, let me get some space. So this graph, this function e to the x. So let's say this is a really long interval from 0 to 2. This function sort of looks like not even close, does not reach the x-axis. Looks like that, right? So the area I'm trying to find is this, underneath this long tail here. I want to divide this up into 4 equal pieces, right? So Here are my rectangles that I want. Remember, I wanted midpoints. So how long is each one of these little rectangles I'm making? Or how wide, I'm sorry. Yeah, so these are all gonna be 1/2 times 1/2 times 1/2 times 1/2. So they're all gonna be 1/2 long because my full length is 2 units and I want to split up into 4 equally wide pieces. How do I find this value right here? Or I guess what X value is that if I want the midpoint of that interval? So this is 1/2. So these X values are 1/2, 1, 1.5, and 2. So if I want midpoints of each of these subintervals, I want to find that point, that point, that point, and that one there. So what X value am I sampling from that first interval? What was that? 1/4. Yeah, what's the midpoint of 0 and 1/2? That is 1/4. What's the midpoint of 1/2 and 1? 3/4. What's the midpoint of 1 and 1.5? That's not between,
Oh, 1.
yeah, 1.25, which is, yeah, 5/4. And then finally, between 1/2 and 2 is 7/4. So those are how I'm going to get my heights: f of 1/4, f of 3/4, and so on. And my base, my widths are all going to be the same. They're all going to be equal to 1/2. So that's, if you compare that drawing on the top there to the summation we have on the very bottom there, hopefully you'll be able to see that those are essentially the same thing. Any questions? All right, yeah, this one deserves more time than what I have left. So let's do this. Let's go ahead and stop there.